Estás viendo Canal América, televisión dominicana para el mundo.
A Time for True show is sponsored by the Office of Dr. Bernard Fialkoff, a periodontal, dental implant and laser specialist in New York City, for over 40 years. Dr. Fialkoff was honored by the International College of Dentists and Pierre Fauchard, and received the Presidential Lifetime Humanitarian Honor from the White House. Call us at 718-229-3838.
Sometimes life can be so damn hard. You don't know where to go. Everything keeps falling apart. Yeah. You try to do your best, but only God knows that you've given everything you've got, but the world takes you down. You just keep moving on. Let your fears.
Welcome to A Time for True show. I'm your host, Dr. Bernard Fialkoff, and it's a pleasure to have you back on our program. And happy Memorial Day, a day when we give tribute and acknowledge all the men and women who served our country and gave us the freedom. And very interesting enough, our guest tonight was also in the Air Force, and we're very lucky to have with us Dr. Sam Miller, PhD. And Buddha, if we put his pictures up on the screen, I want to get right to him and introduce Dr. Miller, who graduated with an honors in weather forecasting from Chanute Air Force Base. He received a BS in physics and graduated summa cum laude, a Master of Science in Earth Science Oceanography, and a PhD in Earth Sciences from the University of New Hampshire. He also earned an MBA from Plymouth State University. And prior to joining the faculty at Plymouth State in 2005, he worked as meteorologist for the U.S. National Weather Service in the Alaskan region, Anchorage Forecast Office. At the University of New Hampshire, he served as an instructor, lecturer, and research scientist for the Climate Change Research Center, and was a research scientist and programmer for the Ocean Process Analysis Laboratory. He worked as a weather observer for the Peace Air National Guard at the base weather station in Portsmouth, and as an active duty weather forecaster for the U.S. Air Force in Adana, Turkey, in Plattsburgh Air Force Base, New York, Travis Air Force Base in California, and Loring Air Force Base in Maine. In addition to teaching at PSU, Dr. Miller is a certified consulting meteorologist and serves on the MAS National Board of Meteorologists. And Buddha, if you will, let's bring him up live on the screen and a warm welcome to Dr. Samuel Miller. Thank you for being with us, Dr. Miller, on Memorial Day.
Thank you, Dr. Fialkoff.
It's a pleasure to have you with us. And, you know, I know you guys take a lot of heat in meteorology, not to make a pun, but, you know, I know sometimes myself, if I went skiing or I've had somewhere to go and changed my trip, that you, as I do in my own profession as a gum surgeon, we take a lot of responsibility. And, you know, first, I'm sure people have a lot of questions as to why did this happen, or why couldn't the forecast said this and then this happened. So first, let's start out at the beginning. And I want to ask you, what's the difference between weather and meteorology?
Okay. Weather, to put it simply, is what you see out the window. Is it raining? Is it windy? Is it cold? Is it warm, cloudy, clear? That kind of thing. Meteorology is a study of the underlying physical mechanisms in the atmosphere that produce that result.
Very true. And so now, I would think that probably since the beginning of time, that mankind, was trying to get a handle so he could plan, I suppose, so he could build or know when to build or know when to raise his crops or his cattle, whatever. So I'm curious, how far back in history does this thinking about the weather go?
Well, it's an interesting question. When I was writing my PhD dissertation, which had to do with coastal meteorology, in particular the sea breeze, I dug into this history a little bit and tried to understand at least when the earliest thinking about that aspect of meteorology occurred. And the oldest reference I was able to find was from 480 BC. And it was by he was an Athenian general who grew up as a young fisherman. And he understood that just at the right moment in the afternoon, after the sun had been heating up the coastline for just the right amount of time, that the wind would reverse and the sea breeze would start to blow inward. Rather than having the wind blowing away from the shore, it would suddenly reverse, start blowing towards the shore. And he was able to use that knowledge in a sea battle and defeat the other side because of the difference in the way the ships were constructed. There is it's a slightly later, about 150 years later, Aristotle, of all people, wrote a treatise on the weather in Greece. He got most of it wrong, but at least he was trying. And then about 40 years after that, a philosopher named Theophrastus wrote a book about winds and weather in Greece, and he got most of it roughly right. He couldn't explain why things behaved the way they did, but he was able to at least make some kind of a quantitative description of what was going on there in terms of weather. So roughly back to 500 years BC, but I'm sure people have been thinking about this for a lot longer than that. It really wasn't until about 150 years ago that we started to get a handle on how the atmosphere actually works. So most of our modern understanding of what actually drives weather as we know it really comes from about 1920 forward. It
Amazing.
Involved, it's really not that old, but it involved the combination of two different schools of thought. One was from Norway, and these were folks that were applying the German physics of waves to the atmosphere. And then the other was the American School of Meteorology, which was about things you might have heard of, these weather fronts. They were observing these mostly because of telegraph operators along railroad lines that were sending back weather observations with central location. And these two schools were really quite different from each other. They had very different descriptions of the atmosphere. But in 1920, a bunch of these Norwegians got on a boat and came over here and met with their American colleagues and put together the modern understanding, which has held up pretty well. There's been some changes around the edges. Of course, our understanding of the physics has improved quite a bit since then, but the basic outlines of the model come from that point.
Very interesting. It would make sense that the Scandinavians, since they were such explorers, seagoers, would be interested in the weather, being in the middle of the ocean. I can't imagine back in those early times. I don't know how big their ships could have been. And I'm just thinking, when I've been in the ocean, not even far from the coast, and they would be in the middle of the ocean, in the middle of a storm, I'm sure they may have had some choice ideas or words that they were saying to each other. as they were trying just to survive those tremendous storms that would occur in the middle of the ocean. I'm curious. I know in my own field, and it's an interesting name. His name is Dr. G.V. Black. I don't know what kind of name that was for a dentist, but his name was G.V. Black. And he wrote the first textbooks on dentistry. And I'm curious, who wrote the earlier texts on meteorology and the weather?
Oh, there's a list that is too long for me to unspool here for you. But and of course, there are many different aspects. There is descriptive meteorology, which describes things like air masses and fronts and that sort of thing. There is a lot of physics involved, and a lot of the most powerful thinking, I think, has come from there. People like Holton have written textbooks on the fluid dynamics of the atmosphere. That's a pretty big subject, Dr. Fialkov. I don't think we ought to start listing off the titles.
No problem. I was going to ask you, out of all those books written on the subject, how you kind of mentioned a little bit, but maybe just for our lay person out there who's watching the show, and they go, well, how has this progressed? Like, how did this start out? Like when you mentioned at the, I guess, recent times, how has our understanding of that happened and changed over time to present time?
Well, you go back about 150 years, and a lot of people that were starting to think about it quantitatively, because of course that's what it's all about, getting the physics right. A gentleman by the name of George Hadley, who was an attorney, but he was an amateur meteorologist as well. He stood up in front of the Royal Society, and I'll have to check my history on this. I think this is approximately correct. And he said, gentlemen, we can't even describe why the wind blows from the west to the middle latitudes. And so he hit it on the head, as we had a lot of understandings at that point that were very fragmented of small things, but we couldn't describe the general circulation of the atmosphere. We couldn't even describe what makes the wind blow. We didn't have an idea of what the forces were involved. So Hadley stood up and he pointed out this problem, and he created a model that involved heating of the equatorial region by the sun, which led to rising air currents, and then cooling at the polar regions, which led to sinking air currents, and then just connecting the dots. So that resulted in flow towards the poles in the upper atmosphere and flow towards the equator along the surface of the Earth. And that implies that the wind would be blowing out of the north all the time in the northern hemisphere. And that's wrong. And he knew it. And so he stood up and said, gentlemen, this is wrong. Why? And he was not trained professionally as a physicist, mathematician, but there were others that were. And so they began with Hadley's basic model, the one-cell general circulation. And out of that grew a piece-by-piece development. You add the work of people like Gaspar de Coriolis, who was classically trained as a mathematician and understood his physics quite well. And from there, if you combine Coriolis's understanding with Hadley's understanding, you can begin to understand why the wind blows from the west in the middle latitudes and from the east in the tropical region. And that takes us up to sometime roughly at the beginning of the 20th century. And then from there, we began to understand that there were different air masses that had different densities. And at the edges of those air masses were something that we call fronts, boundaries of strong density gradients. Added to that was other work by people like Nicholas Carnot, who gave us a model of convection, vertical motion in the atmosphere, which is something that I teach and I've written a textbook about. But adding one piece on top of another, and into the 20th century, a modern understanding of something that we call vorticity. There are many others. A modern of the microphysics of clouds and water droplets. Of course, we have to have an understanding of atmospheric electricity. That plays a role.
And I'm just asking a question. do you want to put up some of the images that you've sent to kind of describe this to the viewers? I know we have them in sequence for you, so just let me know whenever you want to put the first one up, or.
Well, I think one of the questions that you wanted to ask me a little bit later on was, how do we know what the atmosphere is doing right now?
Okay, good.
And so what you could do would be to maybe put that first image up on there, and I could talk people.
Let's do that then. Buddha, let's put on the first image for Dr. Miller, and we can see what weather is doing right now. I mean, I know it just rained here pretty heavily in the afternoon, and then it stopped, and here we go. Go ahead.
All right. So again, I apologize about that strange dark line extending from the Midwest into across the southern Great Lakes there, but I don't know. That wasn't in the image that I sent you. Something came up there, but that's all right. We're quantitative scientists. We take a lot of measurements. We do this on a more or less consistent and constant basis. And this map shows North America, obviously a little bit of South America, Central America. But the white dots on this map represent weather observing locations. And these are surface stations. You can see there are some in Hawaii. There's one in Bermuda as well. You can see them along the Antilles. And so on a more or less constant basis, we are measuring what's happening in the atmosphere in terms of temperature, wind direction, pressure, relative humidity, cloud cover. It gets measured, the precipitation type and amount. And these are on the surface of the Earth. And you can set these up. Every one of these places used to be populated by a human being. I did this job as a human being in the early 1980s at Loring Air Force Base. I was a human weather observer. That was my job. And I would make recordings of what was going on a fairly regular basis, as often as once every few minutes, usually about once an hour. And then it would be transmitted off to the world and shared generally. So now it's all run by machines for the most part. There's a few places that still have people working there, but they're automated systems that were built, and they're located at most airports. And you'll notice that there's a concentration of these, for example, on the eastern seaboard. And that's because that's where the dense population areas are, and therefore the most airports. The same thing is true as on the West Coast. You can see it in California, all the way up to the Pacific Northwest. Some of them are located at smaller places. For example, where I live in Plymouth, there's a very small grass runway airport, but they have one of these automated systems. So this is keeping constant track of what's going on the surface of the Earth, kind of measuring the bottom of the atmosphere. If you want to go to the next slide, I can show you another piece.
Sure. Let's go on to the next slide, engineer. We'll put that up. Amazing how many stations exist.
There's about 1,000 of them in North America.
That's unbelievable.
All right, these are upper air stations. So we have to, just measuring the bottom of the atmosphere is not enough. We have to measure through the third dimension, the depth of the atmosphere. And for the most part, this is being done by weather balloons. So they're called radiosonde balloons. They usually weigh about 1 kilogram. They're filled with hydrogen, although the world is changing over to helium. Excuse me, the other way around. They're filled with helium, but the world is switching to hydrogen because we're running out of helium. And attached to it is a small box about this big that has a radio, a GPS, and some sensors. And these are released twice a day here in the eastern part of the U.S. and during daylight saving time. That's at about 8 in the morning and then again about 8 at night, so 12 hours apart. And they take measurements through the vertical depth of the atmosphere. And they go up roughly to the top of the stratosphere, which is about 30 miles up, measuring about once every 2 seconds and sending back temperature, dew point, pressure, and then we track them with the GPS, and so we can back out what the wind is doing in those places. And once again, you'll notice that they're located on islands as well as the mainland continents, just like the surface stations were. So there are major gaps in our ability to use these direct measurements of the atmosphere because, of course, 70% of the surface of the Earth is covered by water. So these are all done at land stations. The other weakness in this system is that the upper air observations, the vertical depth, it's only done once every 12 hours. Occasionally, under extraordinary conditions, they'll start taking these balloon measurements once every 6 hours. But it's expensive. These things get thrown away. They are one use only. We don't know where most of them go. The balloon rises to a certain height and it bursts. and this thing falls back to Earth. We don't know where most of them go, but just as an interesting aside, the radiosonde devices are designed so that they could go through a jet engine or hit the windscreen of an airplane flying at 500 knots without smashing the jet engine or the windscreen. So they're designed in a way that's deliberately very flimsy. So, I mean, obviously with safety now, the odds of somebody running into one of these things is pretty slim, but, you have to be aware of that. So we get these they're called in situ or direct measurements of the atmosphere, and they give us a partial view of what the atmosphere is doing right now. So it gives us a starting point. We can then apply the laws of physics to these measurements and begin to understand the forces, go from weather to meteorology. We can begin to understand the forces at work that are making things happen in the atmosphere. For example, the pressure gradient force, the centrifugal force, the friction force, the Coriolis force. There are other factors such as buoyancy, positive and negative potential energy. We could go on. There are curvature effects as well, but these are only partial measurements, and they're in the vertical, they're done quite rarely compared to the way they're done in the horizontal. So what we need is additional technologies to do more frequent monitoring in 3 dimensions. So maybe you want to go to the next slide, and I can talk you through a couple of those.
Sure. Let's put up the next slide, please.
All right, satellites. So we, starting in roughly the late 1950s, in a response to Sputnik, the civilian satellite program began. It began under Eisenhower. It really took off under Kennedy and Lyndon Johnson. And the idea was to make a constant surveillance of the entire surface of the Earth, so we could observe things such as hurricanes that are in the middle of the Pacific Ocean that might not get picked up by very many surface observing stations because the ocean is so big. If it doesn't happen to cross an island, you don't even know it's there. So we have 2 different layers of weather satellites. They're on the left here. They're polar orbiting satellites. They orbit at an altitude of about 550 miles, and they go around the world once every 100 minutes or so. So a little bit more than an hour and a half. And they're low. 500 miles, 550 miles is not very far up. And so we can take some very, very detailed measurements with those. The outer layer is called the geostationary satellites. Those are the ones shown on the right. These didn't come along until a little bit later, about 1975 or so is when this system began. And they've been up there more or less consistently since then. So we've got 45 years or so of consistent measurements. And that's taken from geostationary orbit, which is actually 1/10 the distance to the moon. You need a pretty big rocket to launch something up there that high, 23,500 miles away or so. But the reason that elevation is chosen is that because at that elevation, the orbital velocity exactly matches the rotational rate of the Earth on its axis. And so if you put it above the equator, it seems like it's hovering there. So you can, and then in the next slide, I can just show you where some of these things are. We are not the only people with geostationary satellites. If you want to bring up that next slide, this was something that I put together for the course in satellite meteorology that I teach to our grad students. There, that looking down on the North Pole of the Earth, and the black ring is the geostationary orbit, and each one of those little colored dots shows where the geostationary satellites are.
And those are all the different countries. Amazing.
Well, right. This is necessarily an incomplete picture, right? There are many, many other satellites on geostationary orbit. This just shows those operated by the major space agencies that are cooperating through the World Meteorological Organization. So all those there.
I wanted to say something, because with the world in so much conflict, it's very interesting that your organizations are cooperating. So I'm just curious, what governments cooperate with this system of satellites?
You can see the list there on the left. All right, so the United States, the European Space Agency, Japan, India, China, South Korea, and Russia. Those are the
Very
major
interesting.
ones.
Very interesting. You know, it's funny because I want to ask you something about the weather, but I wanted to make a comment that it seems like if we can get something big enough that we all want to happen, maybe we can get some agreement on this earth. And I know you and I are going to be doing a show on climate change, which is a pretty big topic, but let's stick to meteorology for right now. And this is so interesting. We're getting near the end of the show. I want to make sure we get to a point with this for our viewers. So you're saying that we have the weather balloons, we have these 2 ranges of satellites, we have these stations. Now, how does all this information get put in so we can get some kind of idea what's going to happen on the East Coast tomorrow? How does this work?
Okay, you left out radar, which is another network. But okay, let's skip ahead. Now you're talking about weather forecasting. Where do weather forecasts come from? All right. So we get all these observations from the ground, from weather balloons, from space, from weather radar. We even incorporate some data from commercial airlines, which have a system called AMDAR, which is constantly measuring the weather and sending it back. So we've got those measurements as well. And we can get a kind of starting point, the initialization field of the atmosphere. And then what we can then do is we can regrid the data. So it has to be assimilated into a physical model of the atmosphere. And then we can apply the laws of physics, which are in the form of equations. And we have to understand what all the flaws are with that and places where it can go wrong. And believe me, we work on that stuff a lot. But one of the terms in those equations is time. And so if you can kind of isolate that term, you can use it as a kind of dial and turn this sort of model, this numerical model of the atmosphere forward in time. And you can see what it'll look like 6 hours from now, 12 hours from now. You have to be careful as you're doing this because there's a lots of built-in uncertainty and the error grows exponentially. There are ways that you can manage that and try to understand the amount of uncertainty that are involved. But we can then see, beginning with the meteorology of now, we can get a look at our best guess based on physics of what the meteorology of the future will be. And then from there, we can back out what the weather's going to look like outside your window at a given point on the surface of the Earth. Now, this is a very complicated problem. It's fraught with errors, and it's the kind of thing that's still a intensely human enterprise because these numerical models are just tools. They're like a smart calculator. You get a good experienced weather forecaster, people that have been doing it for 30 or 40 years like me, they understand when the model's going off the rails and when you have to switch to something different. And there's a lot of judgment and experience that goes into it. You have to make mental adjustments to the results of these numerical models. And there's a lot of other additional processing where you can crank in some climatological statistics. All of these are just tools. Ultimately, it goes into this thing up here inside your brain box, which puts all this stuff together and reasons through what the best or the most likely outcome is going to be at various points in the future.
Well, I got to tell you something. I want to tell you something, Dr. Miller, that I wanted to tell you. Now that I've got a little more of a handle, and probably our viewers probably saying, wow, I didn't realize there was so much involved. And when they, because you guys do take a lot of heat when the weather forecast is wrong. They love you when it snows and everybody gets a snow day. Doesn't matter what you said. And, so I can totally understand that. But it's really interesting to get the complexity of what's going on. And then the reality is that meteorology is a developing field. It's still coming around. It seems like it's not even in its adolescence yet. Maybe it's in an adolescent period, hasn't even gotten into like adulthood where you really are good at your profession. I'm talking about my own. I'm not talking about meteorology. But, I think we need to be a little more forgiving then of our meteorologists all over the world. But from what I can see that I really loved about your talk is the ingenuity of man, the desire of mankind to do something positive for the globe, not just for one person, because obviously the weather affects food, affects heating oil, affects the people in Chicago. I was up there and I almost froze to death walking a block, going to Northwestern University by the lake. And so, I want to thank you. We ran out of time, but I want to ask you something. If you could give just a 30-second to end the show, what final comment do you want to leave our viewers when they watch this show and they get to the end of the show and they go, this is your final comment on meteorology and weather forecasting? What would that be?
We are engaged in trying to predict the future state of a non-viscous fluid that is trapped in a gravitational well in a spherical planet that rotates on its axis once every 24 hours and is unevenly heated seasonally because its axis is tilted 23.5 degrees from the vertical. There are many, many dynamics within that system that we understand well. There are some that we don't. We're learning a little bit every day. And the challenge of trying to predict exactly what's going to happen at a given point on the surface of the Earth 12 hours into the future, we're getting better. We're pretty good with 12 hours. We're pretty good with 24 hours. When you start going out past that, there's going to be growing uncertainty. And one of the things that we're working on as meteorologists is how to better communicate that uncertainty to the public. We could use your help. There's a program called the Spotter Program.
Yes.
And I'm a spotter. You can become a spotter. Contact your local National Weather Service office and ask them how to become a spotter, and they will appreciate it.
Well, thank you so much. This last statement sounds like a family party. You never know what's going to happen. Some explosiveness may occur, or we may be right on the money, but at the end, we still go on to continue. Thank you so much for being on the show. I really appreciate it. Oh, you're quite welcome, and I hope you've enjoyed it, and we're going to have a little more kindness and optimism for those folks trying to predict the weather for us. I know I have a little more understanding now. Have a very good night, and I wish you well on this Memorial Day.
This show was sponsored by A Time for Truth Foundation Incorporated as a community service.
Sometimes life can be so damn hard. You don't know where to go. Everything keeps falling apart. Yeah. You try to do your best, but only God knows that you've given everything you've got, but the world takes you down. You just keep moving on. Let your feet